We're going to go ahead and take a look at quantitative data. And we're going to focus today's or this lesson mainly on the shape of that data and how to find the center of that data. So those will be the main things that we'll look at, but we'll also look at ways to display that, visualize it, and we'll look at outliers. So we're going to start off by looking at 2011 Hollywood movies. Now, here's an infographic on the left about that if you want to look at that more. However, we're going to focus mainly on this table. So on the far left here, you have all the different movies listed. You have the studio that produced that movie listed. We have the world gross right here, and that's the one that we're really going to focus on for the most part during this lesson. So we're going to look at a dot plot. So each dot down here represents one of the movies. So over here, we have the Harry Potter movie, we have the Transformer movie, and we have the Pirates of the Caribbean movie. So each dot represents the gross for that movie. So here we have a histogram. You might think a histogram and a bar chart are somewhat similar or the same. Well, they're not. Yes, they both have bars in them, but a bar chart has categories going across the bottom and always has a space in between the categories. A histogram has, because we're dealing with quantitative data, has numbers going across the bottom because we're dealing with quantitative data. So over here, the height of this bar is 1, and that's because there is only one movie that was between 1200 and 1400 in their gross, and that was the Harry Potter movie. The height of this bar here is 2 because there were two movies in that interval between 1000 and 1200, and that was the Transformer and the Pirates of the Caribbean movie. Now over here, that's where most of the movies are, between 0 and 200,000. And the height of all those of this bar is a little bit more than 100. If we go back here, if we take from 0 to 200, so 0 to 200, from 0 all the way to 200, if we count up all these little dots here and added all those dots together, that's where we get the height of this bar. If we count up all the dots from 200 up to 400 and count each dot and get that, that's the height of this bar right here. So the height of this bar represents how many data values fell in that interval, in this case between 400 and 600. So once again, bar charts deal with categorical data, and the x-axis, the horizontal axis, has categories, not a numerical scale. A histogram is quantitative data, so the x-axis has to be numeric or dealing with the numbers because we're dealing with data that is numbers. Categorical data, the number of bars corresponds to the number of categories. For a histogram, the number of bars can vary depending upon your interval, how wide you make each bar. Or sometimes your software will do that, and the number of bars is not fixed, it can vary. Where the categorical data, oops, sorry about that, it's fixed for the number of categories. We also have shape of histograms. This first one we would say is somewhat symmetrical because we can pretty much cut it in half and each half is the mirror image of each side. We also have this one here which is skewed, and this one over here which is skewed. This one is skewed to the right. It's skewed to the right if the tail goes to the right. It's skewed to the left if the tail goes to the left. So if it's bigger on one side and smaller on one side, whatever direction the tail goes to, that's the direction of the skew. We also, besides having symmetrical and skewed, we can have bell shape. A lot of data, especially when we start dealing with samples, will end up giving us a bell-shaped distribution. For the most part, if you look at an old-fashioned bell, like a Liberty Bell, it's high in the middle and has two little flanges or things that flatten out on the sides. So here's a bell that's kind of tall and thin, but here's another bell shape that's kind of shorter but wide, but still considered bell shape. Our sample size we refer to as n. We also let x's and y's represent our variables that we're dealing with. Now, if we have more than two variables, you would use more than two letters. We're going to have x1, x sub 2, x sub n, and so on. So as we look at this one here, our x sub 1 is the world gross for our first movie. Our x sub 2 is our world gross for our second movie. Our x sub 3 would be for the third movie, and so on. So x sub 4 would be for your fourth movie. When we're dealing with quantitative data, we can actually go ahead and find the average, which in math and statistics we refer to as the mean. Most people are familiar with average, which we will be calling the mean. It's the sum of all those values divided by the total number of data values. So you add up all the values in for that variable divided by how many data values there were. So it's the total divided by how many there were. So if we're dealing with a sample mean, it is x bar, an x with a little bar above it. Just like when we were dealing with the sample proportion, it was p with a little hat on it. If it's from a sample, it's going to probably have something on top. If we're dealing with a mean from our population, we refer to that as mu, which is the Greek letter mu. And notice when we were dealing with proportions, it was just p with nothing on top for your population. Same idea here. It's just a symbol with nothing on top of it. If it's got something on top, it's really referring to your sample. We can also go ahead and take a look at the median. Your median is just the middle value when you order your data from smallest to largest. Now, if it's an odd number of data values that you have ordered from smallest to largest, it is just one value in the middle, and that's what you're looking for. But if it's an even number of data values listed from smallest to largest, you actually have two middle ones. Your median is just the average of those two. Your median splits your data in half. So half your data is above it, half your data is below it. So for this one here, here's our data. Find our mean. Well, to find our mean, we're going to have to take the 8 plus the 12 plus the 3 plus the 18 plus the 15, add them together, and divide by how many data values we have, which is 5. So our mean is, when we work that out, 11.2. Our median, we actually have to reorder these from smallest to largest. When you reorder them from smallest to largest, your median is the middle number. Now, if you had two numbers in the exact center, remember, we had just said that you have to average those two middle numbers. An outlier is any data value that's significantly different than all the rest. Now, there's nothing that's obviously an outlier, but you might consider your 3 here to be an outlier because it's quite a bit different than the rest. But we'll formalize what outliers are a little bit farther into this lesson. So let's talk about the measure of centeredness. Now we had for this data that we were looking at, we had our average and we had our median. Your average, if your data is skewed, is always pulled in the direction of your tail. If it was symmetrical data, your median and your average should end up being the same. Your median and your mean, I should say, not average, should end up being pretty close to the same. But if your data is skewed, your mean is always pulled in the direction of the skew. So, looking at this one here, the distribution is skewed to the left. which measure of center, mean or median, would you expect to be higher? Because it's skewed to the left, your mean's going to be pulled to the left compared to your median. So therefore your median will be farther to the right or higher. An outlier is a data value that's significantly different from all the others. So as we look here at our movie gross for the world, we really have three data values over here that are significantly different than the majority that are over here. So that's our Harry Potter movie, our Transformers movie, and our Pirates of the Caribbean movies. Those would be our three outliers. Now, some statistics are resistant, are really not affected by those extreme outliers. So let's look at that. A median is resistant while the mean is not. So we knew that Harry Potter was an outlier, significantly different. So let's look at our mean. Our mean with that outlier in there is this. Our mean without our outlier in there is significantly smaller. However, our median, when we get rid of the Harry Potter movie, really didn't change all that much. So when you're dealing with outliers, we know that certain statistics are not resistant to outliers. We need to first of all stop and think, was our outlier a mistake? Well, often it's not going to be a mistake. So then you have to decide, is that outlier really part of your population of interest that you're really trying to study and collect data on? Now, once again, outliers are normally not a mistake. So if you do have one or two extreme outliers, run your analysis twice, one with the outliers and one without the outliers to see how the results are different. So once again, for visualizing quantitative data, we can use a box plot, or not a box plot, I mean a histogram or a dot plot. We want to look at our shape, symmetrical or skewed. And we want to look at our measures of center.